Good morning, Seattle. Welcome to Math 152 News. I'm your host, Keisha, bringing you the latest calculus discoveries. Today, we will tackle Aftap's driving dilemma. How far did Aftap drive? To solve this, we will turn to calculus, more specifically, the fundamental theorem of calculus. Let's dive in.
I was driving and tracked my speed, but I don't know how far I've gone. Can anyone help me figure this out?
There are two parts to the fundamental theorem of calculus. The first fundamental theorem of calculus is all about the relationship between derivatives and integrals. It tells us that if we have a continuous function like Aftap's speed over time, we can calculate the total distance traveled by integrating the speed function. Essentially, integration helps us sum up the tiny pieces of distance traveled during each moment of time. This first graph shows the speed function. The curves are plotted with Desmos with shaded area under it from the interval 0 to 4. The area under the curve represents the total distance traveled during this time period. Each tiny sliver of area corresponds to the distance covered in a small time interval. By integrating, we find the total distance.
The funny thing about velocity is that it's constantly changing. So you can't really measure the distance traveled directly because, well, the rate at which that distance is changing is constantly changing along the graph. What you do instead, actually, is measure the velocity over an interval of time. So over a set amount of seconds, so let's just say like half a second, the car is traveling at exactly 5 miles per hour. On the graph, it would be like these little steps. Over that 5-second interval, it's going 5 miles per hour. Okay, so from that, we can find the distance over that 5-second interval. What we do is we take the time and multiply it by the speed. Because going back to the graph, we can represent that distance using geometry. On the y-axis, you have the speed, and on the x-axis, you have the time. That's the same thing that we're multiplying to find the distance. So we can represent over that interval, that 5-second interval, we can just draw a rectangle, and that represents the speed, or the distance traveled over the interval if we assume that the speed is constant. And we can keep doing that over these 5-second intervals. All we have to do is just find the distance and keep drawing these rectangles across the entire graph, and then just add them together. And bam, we have our total distance traveled. It gives us a pretty close estimate of what the distance is.
Hi, I'm Zoe Sweet. As mentioned by our previous expert Aiden, we can measure the area of our said function using rectangles. These rectangles are known as subdivisions. As shown on this graph, which uses 6 subdivisions, this isn't always the most accurate to approximate our area. There's a lot of gaps and areas left unaccounted for. But as we increase the number of subdivisions like in this graph, these areas get smaller and smaller, making it more and more accurate. For usual problems, you bring the number of subdivisions to infinity, which helps us get the most accurate version of this area.
Combining all those rectangles would in turn combine all their areas and give us the total distance. The opposite of any derivative is an integral, and it quite literally means the function has integrated all the small rectangles to make a unified, more accurate area. Taking the derivative of an integral would give us the position function and correlate the area to the total distance traveled. Had this area been considering negative velocity at any given time, that would indicate negative displacement or negative position. In this case, in our example, she would have had to travel backward at that given time interval. In our example, the peak velocity our listener reached was at 2 seconds, where she was heading at 10 meters per second. Now, since this is a uniform parabola where every section of the parabola matched the other side and it was a spitting mirror image, we know that the area, when found through these small rectangles and segments, can be equal when looking at both from the left and the right endpoints. It is around 26 using just this principle.
Now let's talk about the second fundamental theorem of calculus. The second fundamental theorem of calculus gives us a practical way to compute this area. It tells us the integral of a function can be calculated using its antiderivative. By evaluating the antiderivative at the boundaries of time, we find the total accumulated value. In this case, it will be the total distance traveled. In the graph, we have plotted the antiderivative of f-type speed. To calculate the total distance, we evaluate the antiderivative at the final time, subtract the value at the starting time, and voila, we have the total distance traveled. The 2 points used that are highlighted are 0, 0, and 4, 2.66. This is the power of calculus in action.
Thank you guys. By using integrals and the relationship between speed and distance, I now understand how far I've dropped with my car.